Very good. So welcome to CADlab. I believe this is our third meeting. But today we're going to tackle sheet metal. So this is the mini hotbot robot that we got acquainted with the first time. So it's the little guy that plays basketball with little tiny poof balls. But mini hotbot's really cool because the majority of its pieces are made out of sheet metal, just as if pieces of paper that have been folded up. So for instance, don't put it on me here, but for instance, this one big piece here of the flywheel arc, the sheet metal that goes all the way around and then comes up and over and kind of forms this hopper. And I can spin it a little bit so you can get that kind of motion. This is all one big piece. Actually, if you go over to the tree, you can select the parts, that way you can eliminate that one part. So click on, yeah, very good. So all that's highlighted in blue. Actually, I think you clicked on thing. Hit this hopper back. There you go. Everything that's highlighted in green here, that's just one big piece. It's made out of sheet metal that was all folded up, and we're going to learn how to do that today. Other sheet metal parts that are in here are pretty much the entire drivetrain here is made out of 1, 2, 3, 4, 5 sheet metal parts. We'll start with one of these. So in fact, let's start with this here. So go ahead and open that file and we'll spin this around in space. That's fine. Cool. Spin that one around for me. Perfect. So this is one of the components that make up the drivetrain, and it's got this kind of flat base, and then it's got these edges that have been bent up to make it structural. It's as if we put L channel all the way around it, but we're just using the actual material that's there. We bent it up. And the cool thing about sheet metal parts is we didn't have to model this actual bend. What it actually is going to be able to do is it's going to be able to unfold it, fold it and unfold it, so that way we can use the machines. And in fact, we've got a sheet metal tab up here, and go ahead and visit this up here on the big screen, and we'll see how we can unfold it. Hit this flatten button right there. Yes. So you can see how it just flattens it right back out. When you spin it around, you'll see that it's in its two-dimensional state, where it's all one plane. And then you can click flatten again to fold it back up, and it makes all those tabs. So it's more of an interactive model that has a little bit of liveliness to it. So we're going to be messing around with that today. So we're going to make this part. Go ahead and create a new document. And then every single part that we're going to be doing here, we're going to start with a regular sketch, but we're not going to use the typical boss extrude that we've been doing before. So let's go ahead and just sketch, make a new sketch. On the top plane, since we're going to pretend like this is laying down on the table. Cool. And we're going to start by sketching a rectangle, and this represents the outer shape of it, the profile, when it's all folded up. We're going to work in inches today. I personally don't know the raw dimensions, so we're going to play around. We're going to make them up as we go. So let's say that the entire length of this rectangle is 1 foot, so 12 inches. So we'll jump into Smart Dimension. And we'll take that top one and make that 12. And then the height of the next, let's see what 4 looks like. See if those proportions are about right. Yeah, we could probably make it 3. So 12 by 3. I like those proportions. And we'll go ahead and center that on the origin. And a really quick way of doing that is drawing a construction line from one top right corner or top left corner to the other opposite corner. And then the midpoint of that line you just drew, you can make that midpoint to the origin. So click out of your line tool. You don't want to be drawing another line there. we're going to be, just select them both, select the origin and the line, and then hit midpoint.
Girls,
Hey,
how are you guys?
doing well. Cool, very good. So this is the base of everything that we're going to need to do. Typically, if we were going to make a regular model, we would use the feature that boss extrude. But since this is going to be a sheet metal part, and it's going to take more liveliness to it, we're going to have flanges that can bend up and over. We're going to jump, instead of the features tool, the sheet metal tab. Sheet metal tab to the right of features.
I don't have a sheet metal tab.
If you don't have a sheet metal tab, right click on one of these tabs. Right click on them, and then you get an entire drop down menu of things that you can have shown. So for instance, make sure sheet metal is checked. And then it should pop right up on there for you. Is it there?
Yeah.
Perfect. So once you're in your sheet metal tab, you should only have one option really that you can use while you're inside of the sketch. And that's base flange tab. Go ahead and grab that. And it's going to look exactly like in this live area, like you're extruding it, just like we're typically used to. On the left, though, it looks a little bit different. We've got everything that's tuned for sheet metal. So it's asking us the parameters, for instance, how thick, what's the thickness of our sheet metal, the sheet thickness. And in this case, let's use a 1/16 of an inch. And that would be 0.0625 inches. If you ever get into crazy fractions, you can always type 1 divided by 16, and then it'll spit out the actual decimal value. You can also specify sheet metal by gauge by using a gauge table. I don't usually do that since we work with aluminum that usually comes in. We specify aluminum that comes in fractions, but I'm sure there are some gauges there. That feature would come in handy if you're working that way. All these other, we're not worrying about too much because that's a little bit more in the advanced side. If you want to go around Google and play around with that later, but this is all that we really need to specify here, the thickness of the material. And go ahead and hit the check mark. And so now that we've just got this flat sheet of metal, and we're going to add to it. We're going to add flanges. So in your sheet metal tool tab, there is edge flange. It's on the top of this first row of 3. Look at that edge flange. I'm going to get my pointer. Cool. Yep, edge flange right up there. And what edge flange is going to do, this is where the magic happens for sheet metal, is you can click on one of these edges, one of the lines, just like that. Go ahead and grab it. And what it's going to do, and now move your cursor around, lift it up. And what it's going to do is it's adding a flange, for instance, starting at 90 degrees. And you can specify the length of it. Go ahead and click in space just to set it at some arbitrary number. And your flange length, you can change it right over there. And in this case, let's just make it 3/4 of an inch, so 0.75. We've got a whole bunch of other parameters here. This is the more interesting part, where you can change the angle of the flange. Right now it's at 90, which is what we're going to want. But if you wanted to have a flange that was bent at a 45-degree angle, you can rotate it around and see that that's no longer perfectly straight up and down. That's cocked over at an angle. And you can specify exactly what that is. While you're on this view, go ahead and give a nice big zoomed in portion here. Perfect. And if you could orient to the X view for me, and then center it on that. Cool. What you'll notice here is the bend, it added this big radius here, and that's required. That's how the sheet metal will actually bend in real life. Very similar. But you'll notice that we have this overlap, and you can specify what this overlap is. In this specific instance, this overlap is significant because the edge that we drew originally would line up with the inside edge of our flange. So if it was supposed to hug apart tight inside, this would be a fantastic option. But you can change this position by over here with the flange position boxes. You can go ahead and click through them and watch as this yellow preview portion aligns differently with different specifications. And you can get a sense of what each one of them does. Some will look redundant, like they're giving you the same result, but they are in fact different. And when you're going into more specialized uses of these flanges, you'll just click through them all until you find the one that you like. So we won't go into too much detail about what each single one of them do. But in this case, let's leave it just like what we have here, where the outside is going to align with the edge of our part. Now rotate around, that should be the first box. Rotate around, give us a little perspective view there. We've added one flange by clicking this one line, but let's actually go all the way around and click all the lines that go all the way around. And it's going to add a flange every single time we click. And what you'll notice too is that it automatically takes care of the corners. The corners are going to bend really nice and easily. You'll notice that it chops away this kind of awkward center portion where the flanges would have met, and shortens it a little bit, just enough. So that's very good. We can specify more things like custom bend allowances, but until you actually need those features, you can find them when you need them. Go ahead and hit the check mark, because this is exactly all we need right now. And it'll apply it. And it was actually pretty easy. Very cool. So what we can do now is, if we want a really quick preview of what this thing is going to look like when it's all flattened out, we can go ahead and jump up to the sheet metal tab again, and then flatten. That's what we were working with before. And it turns into this cross shape because this line is what we'll bend up to, and we'll see that we really don't want that, that square there. It was smart enough to take that away from us, for us. And you can just kind of bend those flanges up and down. It's kind of fun to play with. Very good. Cool. With that, that's the really basic introduction of how sheet metal works. We could put this right on Mini Hotbot if we wanted to. We might. We can use this in alongside the regular features. For instance, if we wanted to add an array of lightning holes, we could just make a sketch of what those holes would look like and do a regular old cut extrude. So yeah, sure. Let's go ahead and do that. We'll pop. Let's just pop one really big circular lightning hole right here on this outside end, and we can just pop that right through with a cut extrude, and it'll work just the same. And we can tell that to be through all. Very good. Cool. When you flatten it, that cut extrude will stay there, and it'll be just like it's a regular part of the piece. So that opens up a lot of opportunities there for making those really custom pieces that have that ability to bend. A word of caution, though, when you're designing parts like this, they can get very, very tricky. Can you Google an image of a brake press? So the machine that we're going to Google an image of what the machine looks like that actually makes these bends. Because if we were going to bend this by hand, it wouldn't be very likely that we would get very clean linear bends. But that's why we have sheet metal brake presses. Let's see if there's a good illustration of one. Yeah, that's good. Is there a more expand image? So there we go. Oh, that's fine. Looking point to it. So this big lever over here, that one specifically is a counterweight. This little lever here is what you would lift up on. This essentially entire thing is a very simple pivot point where you would insert your flat stack sheet metal here, and then you'd have a clamp that would hold it down. And to bend it, there would be this really big arm that would come up and it would bend it into shape. So it would leave you with this kind of bent shape. So if my arm was the sheet metal, you would have something that would crank it out like that and then leave it in that upwards position. But these machines have limitations. So as you're designing your parts, you can get familiar with how these machines, what their limitations are. For instance, you can't have two angles that would, two folds that would kind of conflict with each other. Do you think you could Google kind of like conflicting sheet metal folds or something? That way we can get some examples of some things of where it would be very difficult to manufacture. This first one looks good. Oh yeah, this is a good one right here. All right, so this is a really good example. Can you go into a more, can you blow it up bigger? Yeah, there we go. Ooh, awesome. So this is a really good example of something that's really dangerous with sheet metal. In SolidWorks, it gets really easy to design a part that looks like this, right? It seems like you could just, extrude a little bit that goes pretty far up here, and it would just perfectly mount something just the way you want it to. We could potentially see how we could make that in SolidWorks. But when you unfold it and you lay it flat and you try to create it again, this is the unfolded version where when this comes down, it's actually sharing material here. It physically can't be folded. This is an impossible part where this material here, when it gets folded up, would have to take this with it, even though this wants to be held behind. You can kind of see how that might conflict. Secondly, if you had, so there's that material conflict you got to be careful of. Is there enough material to go around when you're cutting it? Secondly, when you're actually putting this on the machine, it will bend an entire linear length. So for instance, if this was the machine, it's going to bend everything on this side of where it's holding on to. So in this case, it would actually have bent this extra tongue up too, unless you bent it by hand. So there are a whole bunch of different constraints that you get to know fairly up close and personal when you start imagining how to place your parts on this machine. But we won't go too much into detail there. Let's go ahead and jump back out, because there's a second way you can make sheet metal parts.
Any questions?
Cool. So let's go ahead and jump into a new part. And what we're going to do is we're going to dive in a little bit of last week, what we talked about last week, where this time we're going to create. Actually, Dad, if we can jump back into the mini hotpot assembly. That one really big, complicated part that we had, that was this entire shooter. We're going to make this part, or we're at least going to get a good start on it. So we're going to learn how I got away with making this curved bend that was like a section of a circle. But you can kind of see, at least from up here, how this might be one big flange that we would have added. And then on that flange, we added a flange that went straight up. Actually, you know what? Before we take off from that one part, if we could jump back to that first part that we created. Yes, thank you. Forgot one really cool thing that I wanted to mention. When you, in the tree here, this edge flange 1, that's the feature that I added when we created that flange. Go ahead and hit the plus button there. Drop that menu down. And we'll see that I added 4 flanges, 1, 2, 3, 4, all of them. But it also added 4 sketches. And this little minus sign means that they're underdefined. Go ahead and jump into one of them. Jump into that first one. So hit that edit sketch button in that first sketch. And what you'll notice is it actually, not only did it create that 3D part that could be bent, but it actually created a sketch that you can go in and you can modify. For instance, if you didn't want this to be a really boring straight line, but you wanted it to have a little circular bump here in the middle, we could grab an arc tool. Yep.
So
I would go for 3-point arc tool. Makes it a little bit easier for what we do. And go ahead and somewhere here in the middle, go ahead and add an arc that bows out, just to kind of show the power of what it does. That's good. And make the ends of the arc. Yeah. Make the ends of the arc coincident. Don't draw a second arc. Go ahead and escape out of that. Take one of these points and drag it onto the line. Very good. And then swing this point to the other side and drop that on there too. Cool. And you'll see here that when we're actually going to create a little bump. And before we leave the sketch, we'll jump into our Trim Entities tool. And this Trim Entities tool is actually super duper handy if you haven't been acquainted with it already. What Trim Entities is going to do is it's like a pair of scissors that is going to cut away everything up to certain intersections. So for instance, this point on this line, it's going to cut away what this overlap is, essentially. So when you, there are different ways you can use it. For instance, right now we're in the power trim, so what you do is you click and drag across the line segment that you want to get rid of. So when you click and drag across it, I think something must have gone wrong. Go ahead and Control Z. Click and drag across an empty space with your trim tool.
empty space?
Yep. Start an empty space and drag across the line segment that you want to get rid of. There you go, and it slices it out. And it'll just get rid of that part. It made that one line segment that we had into 2 line segments. Kind of see there that I kind of chopped it apart into bits.
I think what happened is I did it in a different direction. That's why it behaved different.
It behaved different for you because you started clicking on the line. And when you start clicking on the line, it'll trim to where you started to click, which made it a little bit different.
Okay.
Very good. So with this, we could fully define it if we would like. But for the sake of brevity, let's go ahead and just leave this sketch. And we'll see here that it actually added that bump. And when we go and we flatten this part, that bump comes with it. So we have the power to change the contour of the edge bends after we've created them. So we have to create them, it'll make it a boring square, and then later we can go in and add personality or add more functionality.
Or holes.
Yep, holes, or you can make it at an angle, or a whole bunch of things. You can just make it in your own sketch. Okay, so any questions on how we were able to do that? In which case, what we're going to be working on now, go ahead and jump back to Mini Hotbot. Cool. We're going to be creating this green part now, and we're going to be diving a little bit back into last week of how we were able to create designs from scratch. So what I would like us to do is we're going to, given only a 4-inch diameter ball, we're going to create something that's functional that would have this general contour to it. So with that, we'll jump into that part that we created, that fresh new part. If you haven't created one, go ahead. And we're going to start a new sketch, this time on the right plane, since we're going to be looking at it from a side view. I think a good thing to start with, the one thing that we do know is that our ball is going to be 4 inches in diameter. So let's go ahead and draw a ball in there. A 4-inch diameter circle is going to represent our ball. And we can smart dimension that 4. Don't forget to put yourself in inches. Down there at the bottom. Very good. Cool. So with that, we've got that one ball. The second most important thing to the ball and what should sit on the origin is the flywheel that this ball is going to come in contact with. It's going to be this fast spinning flywheel that the ball is going to rub up against, and then that flywheel is going to rev that ball from the shooter out and soaring into the air. So let's slide the ball off of away from the origin, so it's not holding onto it too tight. And then we'll drag another circle, since our flywheel is going to be around. In this case, it's going to just represent a wheel. And this is going to be 3 inches in diameter. Let's go ahead and smart dimension that flywheel circle as 3 inches. Very good. Now, when the ball comes in contact with the flywheel, it's going to be touching their tangent. We're going to simplify the problem so that it'll just be tangent. So go ahead and create, select both of these circles and make them tangent to each other. Very good. Cool. Sweet. And I think the next most important thing is now we can see the ball's path of travel as it goes all the way around. The next most important thing is, what about when the ball is released? What position is the ball going to be in when it's released? And in this case, for mini hotbot, it's going to be at a 45-degree angle. So, for instance, if the ball started down here, it got caught in the flywheel and then shot across this way, the ball would let go somewhere in this vicinity. Very good. So let's draw a couple. We want to define this position of this ball here. So let's take a line, and the angle that this is going to be at is going to be from the. Let's draw a line from the center point of both circles. Center point of one circle to the other circle, and the angle of that line is going to represent is the angle the ball is going to be released. And we're going to draw a second line too that's horizontal to give us something to reference. Very good. You have to make sure that line's horizontal.
All right. Hey, just a second. I'm doing something really stupid, I think.
Oh, no problem.
Or I'm not doing something.
Mm-hmm.
I can't actually move the circle.
Yes. This is always a tricky thing. So to move a circle around in space, you have to click on the center point of the circle, just that one tiny center point. You could change a circle's radius or diameter by clicking on the round edge, but since we defined it as 4 inches, it can't move. So by doing that, we can't change the radius or diameter. But moving the center point will move the entire circle. Very good. So with that, we've got this kind of reference horizontal line. Let's jump into our smart dimension. And we're going to add a smart dimension between both of these lines that we drew. And when you click both of them, it changes into an angle smart dimension, since they're already at an angle at each other. And we're going to go ahead and type in 45 degrees is what's going to separate those guys apart. In Smart Dimension, it's important to select the Smart Dimension tool first, and then what you want to Smart Dimension after. When we're adding relations, it's the other way around. So it's a little bit confusing, but for Smart Dimensions, we select the tool first. Very cool. So now that we've got the ball is turned black, it's in position. This is the point in space when the ball is going to be released. Just so that our drawing is a little bit clean, let's take these two reference lines that define the angle, and let's just make those construction geometry so they're not quite as bold as what the geometry that actually matters. So you can do that by selecting it, and then coming over to the left-hand side and clicking this box that says For Construction under the Options menu. 7. All right, very good. So now we've got the ball in this last position. This gives us enough information that we can start to draw the curve that the ball is going to be squished up against. So let's jump into our arc tool. Excuse me. Yep. And we can use let's use the center point arc this time. We could use the 3-point arc or any of the arcs, but in this case, this is a good application for when you might want to use the center point arc. It's going to ask you to start drawing at the center, and because the ball is going to be traveling around the flywheel, the center of this outside wall is going to be at the flywheel. So we're going to start drawing our arc at the center. And drag it all the way out so that's on the outside edge of this ball, and start clicking somewhere down there. And just get it approximately where it's supposed to be. And go ahead. And then draw the arc until it meets this edge of the ball. Very good. And this is a really crude estimate of where our how our ball is going to be traveling against, what our ball is going to be traveling against. It's crude because we haven't defined it in space yet. But it's already concentric to our flywheel. If we had drawn a 3-point arc, we would have had to make it concentric with our flywheel. But the next thing that we need to have it do is be tangent to the ball. We want to make sure that it runs nice and smooth against the ball. So select this edge wall and the ball itself. And then go ahead and make those 2 tangent. Cool. Very good. And what we'll notice is that the endpoints of our arcs, it's not quite defined. So this bottom one can still slide across, and in fact, our top one can too. So go ahead and click and drag the top one so you can see it move around. Yeah, so it can still extend farther and lower. And this would change our angle of trajectory when it lets go. For instance, if we had left it here, the ball would travel at an angle that would look like this. So it would be a little bit higher than 45. Or if we dragged it down lower, it would go straight up. But we want it to be over here. Or this point wants to be coincident with the edge of our circle, the ring of our circle. So select both the ring of our circle and the end point of our, the upper end point of the arc that we just drew, and make those 2 things coincident. And so that'll put that that end of our point touching that circle, so it'll release our circle right there at that spot where we want our one to be released. With that, let's zoom out just a pinch and drag this end of our arc all the way onto this side, because we're going to add another line that looks like this. It's going to be tangent. And this is going to represent the ramp that the ball will roll down before it touches our flywheel. So go ahead and draw another line. Very good. We want our line to be joined with this edge of our circle, or of our curved pathway. It's going to be the same piece. So go ahead and you can either click and drag this endpoint onto that endpoint, or select them both and hit coincident, or merge. Actually, it'll be presented with merge. And now they're as soon as we've dragged them on top of each other or merged them, they're one unit, and this is one contour essentially. The next thing that we need to have is make them tangent to each other. We want it to be a really smooth transition. So select them both again, the entire lengths of the arcs. When we select them both, we can choose tangent, and it'll make a really nice, smooth transition between the ramp and the point when it makes contact with our flywheel. Right there. Very good. And then what would be next is defining the angle that this is set at. Let's see how 30 degrees looks. So let's jump into our Smart Dimension tool, and just like how we made this original one 45 degrees, click this horizontal reference line and our new line that we just drew, that's still blue. And it'll give us an option to make it whatever angle that we want it to be. And in this case, let's choose 30 degrees. Cool. Awesome. Perfect. So next thing, we're almost done. We can almost hang this up. We just want to add a back wall, a vertical back wall. Let's grab another line segment, start drawing at the end of this point, and just strike a line up. And this is kind of like a backboard. This is the point. This is the back of the hopper. We just need to add that one vertical line. Just for convenience, let's make this upper point here of our shooter and the upper point of our backboard, make them horizontal. That way they'll be at the same level. So shift click them both and make them horizontal to each other. So that way they'll be on the same plane. It'll be nice and flat. It's still blue because we can move it left and right. It doesn't quite know where it wants to live. Cool. So we're going to define that too. We could pick an arbitrary number, or we could use a little bit of logic by drawing in a second ball. For instance, the ball that is just about ready to be fed into the flywheel, but it's waiting. So let's draw a little bit more detail to really figure out where that ball can be by drawing another ball. Just draw the circle, because since we already have the first ball, we can select both circles that represent balls. And instead of adding a second smart dimension, that's 4, we can select them both that represent balls, and we can make them equal to each other. And that's the relation that's right beside concentric. It's the equal sign. So if you're down here, it would be this second to the last one. Or if you're up there, it's right there too. That way, they'll both be equal to each other no matter what. And you won't be able to change the outside diameter without changing the smart dimension. Very good. So let's pretend that this ball is going to be fed into this flywheel. So because gravity, it's going to be sliding across this line. It's going to be moving across that line until it touches the flywheel. So let's make it tangent to that line. Cool. And now you can click and drag that center point, and you can see it on the pathway as it gets to that shooter. You'll notice that the tangent relation doesn't extend to the arc of our circle. It just will continue the trajectory of the line. So it's still technically tangent to the line. Very good. Now, what is stopping? Let's go ahead and drag this ball down here. What is stopping the ball before it hits this flywheel here? And if we jump back to the 3D model, we don't want the ball to be to hit the flywheel before it's ready. So this is the flywheel right here. This is the arc that we were drawing, and it'll let go at this 45-degree angle, and this is that ramp that it's going to roll down. What you'll notice is that we've got another set of wheels here. And these are the feeder wheels that will hold onto the ball and only roll it into the flywheel when the shooter is ready for it, or when the robot's in position to fire. So we're going to add another set of wheels. This one can be significantly smaller. That'll just hold onto the ball. So we'll jump back into our part and go ahead and create another circle. And this circle is going to represent those feeder wheels. It's going to make sure that the ball doesn't go into the flywheel before it's ready. They're kind of like stoppers that can roll the ball through. So let's define that feeder wheel to be 2 inches in diameter. It's a tiny little pipsqueak. Now, we need to choose where it's going to be placed. So let's drag it down somewhere in this vicinity. That's good. And it's going to be, needs to be tangent to our ball. So go ahead and select the feeder roller and the ball, select them both with shift, and make them tangent to each other. That way the feeder wheel will actually touch the ball and have the opportunity to stop it. We just want to make sure that those two are indeed tangent to each other. Very good. With that, another thing that we want to have happen, let's go ahead and move this back down into the position so it's right around this vicinity again, relatively close to the flywheel. And we want to make sure that the ball in this specific case is on the left side of it, I suppose. So you can kind of see how you can move the ball to the right side or the left side. We want to make sure it's on the left side. That way it's not touching the flywheel yet. And we can define this feeder wheel in any position that we want. So in this case, let's just let's grab a smart dimension, and let's smart dimension the vertical, or the distance between these two as being let's do the, there are a whole bunch of different relations or smart dimensions that you could add. You can see this one that goes the radius between these two, or if you slide your cursor a little bit more, it'll go to the vertical distance, and that preview number will change because it's actually different geometry you could define. For instance, if you also went over here, it would define it as the vertical distance between them. But in this case, put it at the off angle. That'll kind of define the shortest length between the two. And go ahead and make that 3 inches. No, that'll be too close, right? No, that'll be good. So 3 inches is good. And there's one last thing that we can do to define it. Jump out of your Smart Dimension tool and click and drag the ball as if it were going to roll into there. You can see how this moves up and down. The feeder roller moves up and down as the ball passes through. And the point where it's highest, go ahead and see if you can just mess around and where the point is going to be highest. It's going to be somewhere around there. And what we'll notice is that if we drew an imaginary line between these two center points of the circle, it would be perpendicular to this line that the ball is rolling across. So let's go ahead and add that relation. Let's grab a line, draw that line, sure, as construction geometry between these two circles. We're done drawing lines. And now we can make that new construction line between the circles perpendicular to what the ball is rolling across, the floor that the ball is rolling across. And that will define that circle in its spot. Very good. And the last step, the reason we wanted to put that ball in there, is it kind of makes sense in hindsight now. When we drag this original problem, this backboard, go ahead and drag that backboard around. As we move it there, we definitely need to be able to hold onto this ball. If we don't want it to squeeze too tight, we don't want it to be way too loose over there. So now we have the opportunity to perfectly size it. So let's go ahead and grab a, okay, here's a little pro tip too. If we were to make a smart dimension between this vertical line and the edge of this circle, go ahead and try doing that. We want to define the edge of the circle. You click on the edge, it just jumps right to the center point of the circle. If you wanted to define to the edge of a circle, you'd have to do something a little bit different. Go ahead and get rid of that. Scrap that smart dimension. We don't want it. we have to make a point. The point is right there, at the bottom right hand of our little geometry drawer up there. The point is going to be a referenceable spot on our circle. And when you hover the point tool on top of the circle, you'll notice these little yellow diamonds that happen in every quadrant, the peaks of every quadrant there. And these are at the horizontal line at the circle center and the vertical line of the circle center. They're kind of like the outmost edges of the circle. And go ahead and add a point to this far left edge. Very good. And then we can draw a smart dimension from that left edge of the circle, that point that we just added, not the circle itself, but the point that we added, because that's what we can reference, and that line. And we can see here now this is at the edge of the circle. And maybe we can give that just half of an inch. Doesn't need very much, just needs a little bit of wiggle room. Very good. So with that, this is a very quick mock-up without very many other constraints of outside the robot of how a functional shooter, right? But you got to be careful, because imagine the ball coming down from up here. It would get squeezed too tight here. The balls couldn't enter from the top. You can kind of see how that might be constricting here. This distance here from the edge of that circle to this line here is but
3 inches.
Is only 3 inches. For a 4-inch ball, that's a little bit of a squeeze. So we have the opportunity with this kind of foresight to change a couple of these numbers around. For instance, we could increase this half of an inch maybe to 1 inch. That buys us another half inch. But we still need to find another, that takes, we need to find 1 inch at least. So we need to find another half inch. So what about if we change this 3 inches? That was this the distance between the flywheel and our circle. And go ahead and change that, 2.5. Looks a little close. Maybe we can bump that to 2 3/4. Still doesn't quite buy us everything we need. So what if we change this 2-inch flywheel to 1 inch? We found a really tiny 1-inch wheel. Oh yeah, that looks nice. Now I wonder, what would be the distance that we have? Do we need to buy any more?
Is there any reason why you don't just make that smart dimension 4 inches or whatever you need it to be?
Yeah, we can do that. We can set up our file to do just that.
3 3/4. So.
Let's do that. Instead of defining this 1-inch distance for this maximum distance here, to take care of the problem really quickly, we could delete that 1 inch and then add a smart dimension that just goes from the edge of this circle to this line and make that 4 inches. But you got to be careful because right now we're going to the center point of that circle. So we can either add a point or we can just add a little bit to that number to make it work. So in this case, we need it to be 5 inches in order to make it exactly right. So a whole lot of different variables that you could tweak to really make this thing work. Cool. Very good. So once you've come up on a set of numbers that you're happy with, what we've done here is we've defined the most important bit of contour, this geometry that comes down, comes back, comes around. And this piece of geometry is what we're going to create a sheet metal part from. We're going to see the magic of it here. We created this side profile view. Trust me for a little bit more, and make all these circles that we've made construction geometry. The only thing that we want to have rigid geometry, the solid geometry, is this one line that surrounds everything. To make things really fast, you can shift click everything you want the construction, and then click the box once. Okay. Yep. Shift click multiple things and click the for construction box. Very good. So now, if the only thing that you have is as real geometry is this outside edge, this puts us in a perfect spot to jump into the sheet metal tab. And we're going to use that same base flange tab function as we did before. But now, since it's not closed, what it's doing is it's actually adding thickness to the line and then extruding that line in its thickness. So go ahead and click this with that arrow just to add thickness so we can really see it work. There we go. Go ahead and let go. So what it's doing is it's taking that profile and it's extruding that as if it were bent sheet metal already. So we define what it's going to be in its final state, and we can unfold it from there. So from here, we can change the thickness of our sheet metal. And we also get a new option underneath the thickness of our sheet metal, is what is the bend radius? For different machines, you can set the bend radius to be a determined number. But for the more intimate machines, you usually set the bend radius to be the same exact thickness as your material. So in this case, change our bend radius to 1/16 of an inch. That makes it healthy for the machine to bend and gives it a really nice tight crop. And with that, you can hit the check mark. And then you can see how it's created that, just taking the profile that we created, that we derived from the flywheel that would be in the middle somewhere, and the ball that would compress it. Yes?
How do you stretch on that? Like, how do you stretch?
Oh, sure. To jump back into that feature. Okay, so it's a little bit funky, this hierarchy. So we'll answer that question, but in order to answer the question, click the X out of this sheet metal. This base flange 1 is the actual feature that we created. The sheet metal feature on top is different. So we can, under direction 1 here, right now it's folded, open that direction 1 box. And this is the more familiar interface that we've got with line going one direction. We can also do mid-plane extrude, so it'll go half on one side, half on the other. And let's do that. And let's set it to be, if the ball is 4 inches in diameter, let's set it to be 4.5 inches wide in total. It gives the ball a little bit of wiggle room as it flies across. And then you can hit the check mark. What we had done before was we clicked the graphic gray arrow that was in there to change it. Just so that we could visualize it. This arrow here, you can actually click and drag it to get an approximate size if you're a visual thinker. But we're just going to type in 4.5 and we'll be happy with that.
Where was the midway mark? Or the midway setting?
Yeah, that is, you change the option that used to say blind to mid-plane. Blind is just kind of, you're just going to extrude one way until you reach this number. You don't really care what's in your way, so you're kind of moving the line. Mid-plane is the exact same, just here in the middle. You're going to do half one side, half the other. And once you have the mid-plane and 4.5 inches, we've just created the sheet metal part. Very good. So we can flatten it out and you can see it unroll. Even the round spot will unroll to make, you can kind of curve that round spot and just keep everything else straight, so you can see how it'll do a sit-up for us. It's always really gratifying when you get to see that happen. I think it's fun. Okay, so we can add a lot of structure to our parts by adding edge flanges. So let's go back into this edge flange tool. Not the base flange tab. That's only when you're starting new things. Edge flange is going to be pretty much your go-to tool after this, after you create your base. And once you've done that, go ahead and click on this edge here and these flat edges. They go all the way across. And we'll add, maybe 3/4 inch depth to those as well.
Shift click?
Nope, you can just click. And a nice feature too is you'll see here that it cuts away here to make sure that you've got enough material, or that you're not using the same material twice here, and it cuts it nice and blank. Very good. Now, you might notice if you try to click the edge of this circle, it won't let you. It won't let you click the edge of the circle. And the reason is you can't bend, you can't have that be a true bend. If you have a linear piece, you can bend a linear chunk. But if you try to bend it into one piece of metal into a circle on its end, that is a lot more difficult and geometrically tricky. It would get very ugly very fast.
You have to break it into flat segments.
Exactly. So you break it into chunks. And we're going to go ahead and we're going to do that next. And I'll show you how I did this in my robot. Go ahead and hit the check mark here to add the linear sections.
How long is it?
They can be 3/4 of an inch long. Yep. Very good. So now if we had a curved section that we wanted to have tabs across to make it more structurally stable, let's jump across into our robot and we're going to see what we did for the 3D one. So if you zoom in a little closer, you'll see that we've got these breaks. We've got a linear section, and then we've got a break, and then we've got a linear section and a break. And that linear section extends all the way across. So really, we don't have a curve. We just have a lot of linear sections that kind of average out to be a curve. And that's a really handy trick that from a distance, you'd look at it and it would be just a perfect section of a circle. Functionally, it's a circle, but geometrically, just linear segments. So let's jump back into our part, and we're going to create that. And edit the sketch, the original sketch that we made out of our base flange. So drop open our base flange here and edit sketch 1. This is the last thing we'll be tackling on our part today. So we know for a fact that just having this geometry be extruded is giving us some problems. We can't make an edge flange with the arc. So what we're going to do is that doesn't help us anymore. We're not going to delete it because it's adding functionality to our sketch. So we're just going to make it construction geometry. So select it and add for construction. Deleting it would underdefine our sketch, and it's actually very helpful. So what we're going to do, since we need a lot of linear sections, we're just going to create a series of lines. So jump into the line tool and start down here. Yeah, start right there. Click once and just kind of follow this pattern. Click once on the edge and then click on the circle again. And then click on the circle again, bring it over, click on the circle, bring it over, click on the circle again. And what we're doing is we're following the contour that we had specified before, and we're just cheating it a little bit by simplifying it or making it into lines. And do it, at lengths that feel good to you. Add as many as it takes till you get to the end. And then make sure you click the end point when you do reach the end. And you can escape your line tool once you've gotten to the end. Is it giving you grief over here?
Yeah, I was trying to make all the sections equal. and now over-defined.
Right, so there is a trick to that. Get it and delete that one equal that's at the end. I'll talk about that once we're up here. So Steve had the right track. We're going to make all of these segments equal to each other. Before we get started, if we select them all and we tell them to be equal to each other, every single one of them all at once, SolidWorks inevitably kind of freaks out in its current, in this current version. It'll freak out where it'll, in its programming, it'll make them all equal to each other. And then once it reaches the end, for some reason, it thinks that this cannot be equal to the rest of them. It creates an invalid geometry. So the trick to getting around it is to select them all except for one. So select all of them except for this end piece. And you can make all of those equal to each other. Just make sure you leave one behind. And then go ahead and make those equal. And now it's done the majority of the hard work. And now that it's done the majority of the hard work, it's easier for SolidWorks to think about making them all equal when it just has to control one last one. It's kind of the way they've written how the equals tool is created. It's how they've written that code is a little bit buggy in this specific instance. So now select any one of the other ones that you've already made equal and shift click that last segment that we haven't yet made equal and make them equal. And you'll notice that they all turn black if they have all been selected because they are truly equal to each other.
I'm still getting over-defined when I do that.
Okay, I'll jump on over. Once you've done this, you can leave the sketch. And you'll see that their segments have been broken up. If you missed one, go ahead and jump back in if you want. Oh, it's looking good.
Yeah, except I don't have the equal on the left.
So there must have been, I think this is the same kind of thing that we've got up here. We have some extra relation that's happening. For instance, on this one, we've got a horizontal relation.
Oh, okay.
And that's what's giving us grief here.
I have perpendiculars.
So when we were drawing all of those lines, somewhere SolidWorks was trying to be smart and add an extra relation that we really didn't want. So go ahead and do a quick check. You might find that your equals might have been messed up. And you can create, add that equals back in.
Particularly, I can see what a relation actually is. Like, I want to know, this says perpendicular, I want to know, well,
Which ones?
oh, it's coincident, never mind. Okay. Oh, well, yeah, they should be.
Mm-hmm. Yeah, the endpoints, an endpoint should be coincident to the arc.
Well, they should all be coincident, all the points.
Right. Looks fairly good. Can you try cookie and drag me on one of those points?
Yeah,
This
I've changed all that, I deleted all those coincidences.
Okay.
I was thinking they were,
Yeah. Try putting them back in. Once you've got this geometry all figured out, you can go ahead and leave your sketch and it will apply it into 3D. And now that you've got a whole bunch of these linear segments, go back into your base flange or your edge flange one down there. There you go. And hit the edit feature, and you can go back and you can add more. So instead of clicking one smooth arc, we're going to click each one of these linear segments. And it's going to add all of these flanges for us.
Purple tongue.
Cool.
Whoa.
Oh, I must have missed a few coincidences.
Shouldn't be a problem.
Coincidence.
Now, this is a lot of clicking. We could just do one side and then mirror all that work to the other side. So if we wanted to do that, we'd want to deselect everything on the side that we don't want to, that we want to mirror onto. So just have one side complete. We'll give it a shot of mirroring, and that includes down here at the base. Just have one side complete.
I have a problem making things.
Okay. Yeah, that one's definitely tricky.
I found it worked best to turn off coincident on one of the points so it can be off the arc. Then make all the segments equal. That's going to push that point off the arc. Then go ahead and make it coincident again.
Oh yeah.
Yeah, I do the same thing. Yep.
Go for it.
Yep. I can see that.
That one is really.
Ah, okay. So that means that there must be some sort of extra relation that's being added to it. So looks like that one's okay. Keep moving around.
Oh.
Ah, perpendicular. Get rid of that guy. Yeah, there it is. And now, look at that. Perfect. Now you should be able to make that last one. Look at that. Happy. Perfect. Very good. So once you've got one side completely done with these edge flanges, go ahead and hit the check mark and apply them. Might take a little bit to think about. Very good. And now that you have one side done, we can go into features and then go into mirror, which is right over here next to shell and underneath intersect. It's a tiny little button. Yeah, right there. And then it's going to, we can, under the features to mirror, you can go ahead and jump into that box and click on one of the faces of the edges. Cool. And now what you need to do is specify a mirror face. What's it mirroring about? And in this case, we sketched on the right plane. So jump into the mirror face plane section and select the right plane, because that is the center of our part, because we extruded in the mid-plane. And it gives you a nice preview of your folds jumping onto the other side.
How long is this to be?
3/4 of an inch is a good number.
And now there are two of the different ones are overlapping.
Ah, okay. So as soon as this finishes computing, then we'll show you up here. So what Robert has on his screen is at a joint like this, the flanges are actually overlapping each other. And I think what had happened is because we had two edge flanges being created. So we did this flange first, we applied it, we made it rigid, it's going to be permanent, and then we went in afterwards and we created this one. When we do that, it can't, SolidWorks isn't able to chop away both of them and average them out to make sure that they are not taking up the same space. So what we have to do in the case that you have overlapping ones is get rid of one of the edge flange features that you've added, and then edit the original and add all of the edge flanges in one feature. So in this case, we have only one edge flange feature, and we put all of our flanges on that one feature. Perfect. You got it. Yeah, it's a lot to think about. If you wanted to, these purple arrows that you see on screen, go ahead and just click one. Don't click and drag, just click. And it'll flip that flange to the other side, 180 degrees. So it's still all the same parameters, it's just kind of flipping which direction it goes. And with that, you can hit that check mark. Each one of these flanges has its own sketch, so if you wanted to do something fancy on each one of them or individually, you very well could jump right in. The mirror is in the feature tab, and it is right up here. Yeah. Very good. And that'll let us just do one side and then pop it over to the other. Now there's a, we'll finish that, and then I want to do one last thing to finish this part off right. Very nice.
Right there are little steps of metal.
Ah, it's true. Very fancy. When you, wow, I'm so glad the actual robot didn't look like that in the field. If you zoom in, zoom in really close here, Robert pointed out that we have little slips of metal. And those little slivers of metal are because we, if you just stop pivoting it here, this was the original edge of the extruded base that we had created. And when we created this, these flanges, we told the flanges to be inset. So what we're seeing here is the leftover of the material that this flange is kind of taking up. Lost all context. Yeah, if you go into the edge flange, right? Yeah, what you can see here is this is the edge of the material that we had defined before, and we had set our flanges to be inboard of the material, which leaves this little sliver out. There's no real easy way of getting rid of it in the CAD model. Is there really?
Nope.
How do you do it?
Select the edge model or the edge flange, edit it, and there is a right below where the mouse is. There is a trim side bends.
Do that. That works.
And then
whoa!
There you go.
I like that.
Excellent.
That is awesome. That's fantastic. Thank you for that. I learn something every day.
That's why we like being part of the team.
Exactly right. Teamwork. There is an easy way to get rid of those. Cool. With that, there's one last thing that I think we need to do. If you can zoom out a little bit here. Ignoring how crazy our bar looks because we had fun flipping the flanges. Okay, sure, we can flip it back. Okay. When our ball is moving across here, and it's going to be moving extremely fast as it gets to the end, and then it's going to shoot out and it's going to go far.
How do you mirror the things?
How do you mirror?
Yeah.
Okay. I'll talk to you afterwards.
You're just click on individual.
We should be able to click on the feature
Oh, okay.
instead of each individual one. Yeah. Very good. So when the ball is coming down here and it's going to be zooming across, and then it gets thrown out the front, this last segment here is going to be taking a lot of abuse. It's going to be bent quite a bit, with a lot of force coming at it this way, because it's at the very tip. It's getting all that very most force when the ball is escaping.
And no support from the next one.
Correct, and it has no support for the next one. But what we can do is we have a little fun trick that we can have. If we create a new sheet metal edge flange, go ahead and put an edge flange running across the length of it in the back, and make that 3/4 of an inch as well. But make sure it comes out this back side. Perfect. Go ahead and make that extremely long one, just 3/4 of an inch. And when you hit apply, what that's going to do for us is when the ball comes down, this end piece is going to be extremely rigidized it has this extra piece of metal perpendicular to it that's very hard to bend now. Now it's very difficult to bend because it has support from this flange that we just added. And it's also nice because this flange is coming out, which means that it's not going to get in the way of the ball. It just kind of folds up and out, gets out of the way, but still provides a structure where it's needed. With that, that's a simplified part, and a functional part for having kind of a loop of putting your ball in, having it zoom across into a flywheel, and then get shot out the other side.
That's part about it.
Yes, this is what we've all been waiting for, is flattening it out. And this one will take a little bit to compute because there's a lot going on here. But the most satisfying is when you flip it around, and this is what it would look like when you go to machine it on like a water jet, CNC water jet, or a CNC plasma cutter. If you create this contour, if you then put it on your brake press and bend all of these flanges on the top at once and all those flanges on the bottom at once, and then bend them all up one by one, or in the case of this, this curve, this is so thin that you could probably just bend it by hand to get that curve. What that'll end up giving you is that the exact part that we want in the end.
And this can be a manufacturing challenge. So many points in it.
Yes, I think that is a function of that trim feature that we checked. Usually, if you didn't have that trim feature, the contour would kind of come down. It would come back up and flatten out, and then come back down again.
That was on the edge.
Right. If we the first edge flange.
Yeah, I did a trim on that end flange,
Right.
and it creates a funky little cutout match.
Yeah, it's funky either way. So when it does that, it'll have to recalculate the entire part for us here on the big screen. Yeah, so it gets better because it doesn't go to a point down here inside the part, but it still is going to generate this funky little tab. When I machined it on the plasma cutter, those tabs essentially just burned away because the plasma cutter is very sloppy and has no eye for detail. But if you're on a water jet machine, you might see little slivers left over, especially if you're getting thicker ones like that. But those are easily filed away.
That's just
in the
a
end.
manufacturing problem.
Exactly. Exactly. We don't worry about that too much. Very good. With that, that's a functional robot part that you could really slap on. Slap on your robot and have a functional sheeter that has made out of one sheet of sheet metal, which saves quite a bit of weight and material and can be very, very rigid if it's designed correctly with all these flanges. Way to go, you guys. There it is on the final part. You can see how this is exactly what we've done. And it's on a real robot. Very good.
And of course, you can add attachment holes.
Mhm.
And the way we held onto this is kind of interesting too. If you zoom out, we've got plastic side panels that are actually mounting it hovered in space. So this plastic side panel mounts the bottom plate of the robot itself. And it's got quite the funky little shape to it. But it works really well. It keeps it nice and sturdy and mounts it right above hovering essentially in the air. If you look at the way, this is a small scale version, so I was able to get away with using just plastic to hold it into place. This is the plastic piece. Yeah, you can see down here it would mount to the bottom plate. And then this is the contour of the actual arc as it gets shot out, and this is where the flywheel would end up. And this is the hopper area here. If you jump into Google and you search FRC 67 in 2012, you'll see how I jump into images. Looks like you have to go into more. Yeah, just cool. go ahead and write into this first one. This is the actual hot pot. Should probably give them some credit at some point. FRC 627 in Michigan. They did do plastic side panels on the side here. We can see this is their big flywheel. That's the same exact contour that we created. And they used some aluminum tubing that they welded, and they mounted that rigidly to their frame, their sheet metal frame. Hot usually has a sheet metal frame, just like that first part that we created. They usually have that strategy, that design strategy almost every year. It's very lightweight and still very rugged. It's designed correctly, and you get a feel for it. So with that, are there any questions on what we can do with sheet metal?
How did you cut the plastic panel?
I cut the plastic panel for the half-scale robot that I made.
Mm-hmm.
This is small enough to be on the laser cutter at MakerWorks. So don't tell anyone, but that's actually acrylic. So it is conditioned to shatter. I could have put it on the ShotBot as well, but I didn't want to do the ShotBot as much when I could get away with the laser cutter, because the ShotBot, you have to have tabs to get rid of. A lot of extra tool changes for putting in the holes. I didn't have to worry about internal radii at all. That was pretty safe. But yeah. And let's go ahead and jump into the actual part that we made out of the robot here. Open that up and let's unfold that for good fun. So that's the big part, and it's got a 3-ball hopper instead of a 1-ball hopper like we've got. All that we really did is we extended this back plate out and we just added more flanges. But when you flatten it, it'll take quite a little bit to calculate. It's really fun just to see how these things, to create such a seemingly simple 3D shape, it simplifies or flattens out to be a fairly complicated looking pucker. And of course, when you're going to machine this, all that you'd really have to do to get the flattened profile is just go up to File, hit Save As, and choose DXF, and it'll flatten it for you. And you can save it at whatever file format you want. DXF or DWG are the two more universal file formats for sending it to for computerized machines. I've got a lot of holes in this one. It takes a lot of SolidWorks brain power to figure it all out, evidently. It'll be a great moment when it comes through. You guys have to promise to gasp a little bit and say, wow, how impressive is that?
I want to see it open up one fold at a time.
Ah, that would be fun.
That would be cool too.
That would. Let's see.
It looks like there's a tool that will undo one fold at a time, but you probably have to go through and manually click.
That's correct. And that's what these unfold and fold buttons are. You will be able to, those unfold and fold, instead of just showing it to you, it will actually create a line item in the tree, where if you wanted to, for instance, have a curve, and you wanted to project onto the curve like a string of text, but you wanted that text to read out perfectly without any distortion from the curve, you could have, you could fold it and unfold it at strategic times while you're creating the CAD model. So you can either get text that distorts with the curve, so super long T, but it looks perfect when you look at it from the edge, or when you look at it from the edge, the text wraps around with the curve. And these fold and unfold add little add features to the tree that lets you change the order of operations, essentially, if you're folding. And you can see that actually I did that here, where I created an unfold, and then I put in some cut extrudes. And I did that for all of these holes. So all these holes are actually created at once, even these guys, because I unfolded it made it flat, put all the holes in, and then I folded it back up. And then I put in another cut extrude that does something, and then a fillet that does something else. Well, this has been fun. I don't think this is going to happen anytime soon. It'll be as soon as I stop the stream, it'll go. But any other questions? Anything else? Yeah, there are a lot of other sheet metal tools that I personally haven't had the privilege of messing around with. Hey, there it goes. That took a long time. But now you can spin it around. And you can see this geometry will fold up to create that 3D hopper. So it's a lot of fun, and I cut that out on the plasma cutter, folded it all up very carefully. This pushed the limits of, you know how I was talking to you guys about knowing the limits of your machine? Yeah, this one taught me the limits of the machine very well. When you're talking about this intersection right here, if you can zoom in and blow this up a little bit bigger, just that kind of this, yeah, perfect, just like that. There is a fold here, there is a fold here, and there is a fold here, and none of them are aligned with each other. So there had to be 3 different folds that happened at the intersection of this corner. On most machines that you find, you have to mount your entire part on the bed. So if this is the part that you're trying to bend, your machine that would bend it, it has to fit within the entire machine. So you would have no choice but to have this entire thing that's on the left-hand side of this be bent up at one point. And you can imagine that if I put the part in there like this, I wouldn't want a bend here. That would be bad. But what the thing about the cool machine that MakeWorks, they have a magnetic brake press that doesn't limit you to having to put your entire part inside the machine. You can what is the cantilever? You can cantilever your part on the outside of the machine. Essentially, you can bend just from here to here, and this part is flailing on the outside of the machine, and then only this part that the machine is actually touching gets bent. And you can do that for this. You can overhang this part of the machine, and then you can overhang it here. This one I think I actually bent by hand because there's no way to actually put that on the machine. Because even if I overhung it, if we didn't have the magnetic brake press that let you overhang stuff, this part would be very tricky to bend by hand or bend with a hammer and a straight edge. But it's all about getting to know your material and getting to know your machines. I guess there's one last cool comment, well, since it's 9 o'clock, but just if you notice that you have a bend on your sheet metal, one side bends really, really well, and it's super crisp, super clean. It's just like a continuation of the surface. And then you bend another edge, and then it gets all chunky and cracked and slivered. What that could be, if you actually, if you can zoom into this section up here, yeah. So this could have happened on this machine, on this part, where this one could have been super clean, and then this one could have been super grainy because they're at right angles to each other. A lot of the time when sheet metal is produced, it has a grain to it, very much like wood has a grain. It can be rolled in order to flatten it out. If it's cold rolled or worked material, it's essentially kind of pushed into place, kind of like you're rolling out dough, like you're cooking dough. You're rolling it out and you're giving it a very distinct grain. It's going to be stretched along this way. You can kind of thinking about it as kind of if you had pasta, your entire metal is kind of made out of lots of little pasta strands, aluminum pasta strands, and you're aligning them to go this way. So if you have lots of pasta strands that are going this way, and you bend the pasta strands like this, it'll be a very nice clean bend because you're seeing the edge of the pasta and it's not actually splitting the pasta apart. But when you're over here and you've got lots of pasta strands and they're being bent like this, they're going to break away from each other, and then you'll get kind of like this slivering. There are some, so one side that bends against the pasta will look really clean, and then when it bends with the pasta, it'll kind of break apart and look slippery. And that's just kind of a material thing that's happening on the molecular level. You can get special metals that are designed for bending that don't have as much of a grain, and then they'll have very nice clean bends. But if you want a really fun word, when a material has a grain to it and you can see that it bends really nice, you can, and when it doesn't bend very nice in the same piece at 90 degrees from each other, you can tell your friends that that material is anisotropic. And you'll be like, yeah, you guys, that's what that is. And they'll be like, whoa, and you'll be that cool kid. Yeah. So don't be shocked when that happens. But definitely plan for it, because those cracked pasta bits, when it cracks, that'll definitely be more ripe for failure. So you should, when you're specifying the material to be bought, make sure that it's good for bending. You can talk with the friendly folks at Alro, and they'll definitely let you know.
The other thing that can help that is not to be as tight a bend.
True.
Do larger radiuses in that direction.
Exactly.
Yeah, can you specify? Yeah, I remember seeing that.
Yeah, if you jump into the any one of the edge flanges, actually it might not be good to do it in this part because it'll take forever, as we learned before. If you jump into any one of the edge flange features, you can specify, I told you before to have the bending radius to be a 16th in order to match. But you can uncheck this default radius, and you can specify that to be like a 1/4 inch or a 1/2 inch if you've got the power to do it, or the means to do it. And you can make that radius whatever size you want. Just like that. You gotta be careful too. You don't want funny things hanging off like that. Could be difficult to bend. And
So files are
well, yeah. Good luck manufacturing that. But with that, if there are any other questions, happy to answer. But I think that's everything that I wanted to share with you guys about sheet metal. You guys did a really good job. I love this.
How do you get a larger diameter bend when you're physically bending the piece?
If you're on a machine, brake press machine, for instance, you can usually set the clamp or the fingers to be very close to the edge of where the material is going to be bent, or you can specify the fingers to be farther back. While you can't make sure that it's a perfect radius, when you specify it as being farther back and you bend it up, the material will kind of average out into a general bigger radius if you're not holding it as close to the end, if that makes sense. If you're bending it with hammers, you're pretty much guaranteed a really big radius. Good luck getting it really small, unless you've got an insane clamping system going on for you and a very sharp edge.
So the material comes in here like this, that's your material. And you're bending, and this is the bending piece that's coming up and bending up. Depending on that distance that you need there.
Oh, okay, yeah.
This is, and I'm sorry to take over, Dave, but this,
No, it's perfect.
This is the fixed platen.
Right.
And then you lay your material in here like this.
So it'll bend up like this.
Yeah.
And this is the pivot point running across here.
So depending on where this upper piece that comes down and clamps your material in, the further back you are, the more space you're going to have. And it'll just naturally bend a little bit harder.
Exactly.
There is, of course, a limit. It depends on, it's what, double the size of the thickness of it. Not sure exactly what it is, but it'll execute very cleanly. But, and once you get beyond that, then it really kinks and does some funny.
Right.
But at least you have a little bit of control of it on the manual. If you want something smooth, then you need to go to some kind of dye that we can pound in the engine.
Oh, yeah.
Or do something similar to this to get a large radius like that.
Chop it up into little bricks.
And then kind of hand them these.
Even though this looks really chunky in the CAD model, when it comes out in real life, nice and smooth. So, very good. We've been keeping you guys a little bit long, about 10 minutes after. So, but if you have any other questions, feel free to pull me aside. And just, I'll send out an email to you guys, but we're not going to be meeting on the 8th and the 15th. I'll be out of town, but we'll be meeting next week. Yes. So with that, very good. Thank you very much. See you guys next time.